Okay, today we're talking about the average value of a function. Let's suppose you're in a situation where you're actually recording temperature throughout a particular time period. Say, for example, you're taking temperature recordings every hour over a, say, 4-hour period. And the y-axis is going by 10, so this is in degrees Fahrenheit. Let's suppose when you first make a recording of the temperature, you get 30 degrees. And then after the first hour, you do another recording and say the temperature jumped up to 35 degrees. At the second hour, suppose it warmed up to about 40 degrees. And then at the next hour, let's suppose it got a little colder. This time it's down to, how about 25 degrees? And suppose that you needed to find the average temperature throughout this time period. Well, if you needed to find the average temperature, all you really need to do is take these 4 values and average them. So we had a temperature of 30, a temperature of 35, a temperature of 40, and a temperature of 25. And of course, if we're taking the average, we just need to add these up and divide by the total, which is 4. And in this case, it means that throughout this 4-hour time period, the average temperature was about 32.5. Now, what if we had a slightly different situation, where in this case, the temperature recordings were actually happening continuously? So if we had been recording the temperature continuously, the curve might have looked something like this. Now, if we did need to find the average value of this function, what we should do, take function values and divide by the total number. So for example, you could do some sort of method to estimate, like for example, something similar to the midpoint rule where you take the middle value. Or you could use some other sample points. So for example, here you would be adding up the function values and dividing by the total number of rectangles, which in this case would be 4. If you wanted to take a generic number of rectangles, then you could take, say, n rectangles. That would work for whatever approximation you wanted to do. So for an approximation, the average value would be taking your function values at your sample points, whatever sample points you happen to have chosen, and dividing by n, right? Well, you can write this as the sum of f of x sub I over n. Now let's suppose that instead of making an approximation, I wanted to find the exact average value. Well, for exact, we need to let n go to infinity, right? Because we need to have an infinite number of these approximations. And as n goes to infinity, we'll be hitting the function value exactly. I'm going to write the 1 over n over here. And don't forget, for our Riemann sum construction, that delta x, the change in x, is equal to b minus a over n. So notice how we already have the 1 over n here. We just need to insert a b minus 1 over, the b minus a. So if we put in the b minus a, if we put it there, we just need to put it somewhere else with a 1 over. So I could just stick it on the outside if you like. Then what happens is I've got 1 over b minus a, the limit as n goes to infinity, and then the summation of the function value. And now notice how this whole part here is just change in x, the delta x part. So notice here from the limit on, I actually have the integral construction. So again, if I want to take the average value of a function, I really just need to do 1 over b minus a times the integral from a to b of the function dx, and then it's no longer an approximation, it's an exact value. So now we're equipped to actually state the exact formulation for the average value of a function. The main thing to realize is you just need to take an integral. And then just include this 1 over b minus a part. And that's it.